Before we assert the fundamental theorem of line integrals, let's talk about some assumptions on these curves, vector fields, and their domains that must be true. So one of the things that you may see in some of our definitions, or you may be asked to think about, is that the curves that we are considering must be piecewise smooth. So all that means is they may be made up of pieces, different pieces. So here I'm drawing this line in two pieces, but essentially they need to be smooth end to end. So this is a piecewise function that is not smooth. They will oftentimes need to have continuous partial derivatives, which is most of the time what you guys are going to see will be the case. And then they also need to be connected, and there are two types of connected. There's simply connected, and what we see here are two pictures of simply connected regions, one in 2 space, one in 3 space, versus the opposite of that, which is not simply connected. So these two not simply connected regions have a hole inside of them, or essentially I can draw this curve, and if I contract this curve and try to make it as small as I can, it would be impossible to contract it down to a single point. It would always be tied around that hole. Or in this torus, it's possible to draw a curve that I would not be able to contract down to a single point. One way to think about connectivity is to consider that neither of these two connected regions have a hole that could potentially get caught on a hook. So you'll see that both of these regions, including this 3D donut or torus, they have a loop that could get caught on something, which means they are not simply connected. This, if it got caught on something, it would slip back out. And so it's important for us to talk about piecewise smooth and connected versus simply connected and continuous versus partial derivatives, because we're always giving definitions, and at the start of those definitions, we put some restrictions on our situation. And if those restrictions do not hold, then we cannot apply our definition to the situation. So as needed, we will state these conditions, but I felt it was important for us to especially understand what it means to be simply connected. Now, as we think about our fundamental theorem of line integrals, let's go back and think about our fundamental theorem of calculus from Calculus 1. And that said that if we had some integral from a to b of some little function f of x dx, that we would define that as, and do you remember, we would use capital F of b minus f of a, where little f was the derivative of big F. So the fundamental theorem of calculus basically just said we could take a derivative and then apply this antiderivative concept. So this brings us to our fundamental theorem of line integrals. So as long as we have C, a smooth curve connecting point A from its initial point to point B, the terminal point, in plane or space, parametrized by R, if f is a differentiable function with a continuous gradient vector such that that vector field equals the gradient f, or little f is the potential function for that conservative field on the domain D, which contains the curve, then that line integral is equal to f of b minus f of a. Or rather, that line integral across the curve C of f dot dr is the integral from A to B, my initial and terminal point, of that gradient of f dot dr, which equals f of b minus f of a. So let's look at a short example of what this means. Suppose the force field is given by this function. F of x, y, z, our multivariable function, is negative 1 over the quantity x squared plus y squared plus z squared. We want to find the work done by this force, or this force field, I should say, in moving that object along the path, along the smooth curve, which joins the points 1, 0, 0 and 0, 0, 2. And then we say, well, it can't pass through the origin. And the only reason we're saying that is because the function is not defined at the origin. So any path except for that one undefined value, which again is created at the origin. Well, when we see work, we know that that can be set up with a line integral. And by the fundamental theorem of line integrals that we just defined, what that means is the line integral of f dot dr is going to equal f of 0, 0, 2, my terminal point, minus f of 1, 0, 0, my initial point. And if I plug my terminal point into that original function, I get out negative 1/4. And if I plug my initial point 1, 0, 0 in, I have minus negative 1, which gives me 3/4. So again, visualizing what's going on here, we have these 2 points on the axis, and the line integral along any path, regardless of that path, as long as we do not pass through the origin from A to B, the work that that would take would be 3/4. So as long as that force field is defined as the gradient of F, then we know we can apply this fundamental theorem of line integrals. So that's kind of how this theorem works. Let's prove this theorem, because I know it's probably been a while since we've done a proof, and this one's pretty short. Let us suppose that we have 2 points, A and B, in our region D. Our curve, or our path, is parametrized as we have previously defined for some t value between a little a and little b. So that curve is a smooth curve in my region D, and it joins my initial point A to my terminal point B. So when we think about working a proof, we start on one side, we start with our given, our left generally, and we manipulate it to create the right side. Here, we're going to start with the line integral definition. So we've got our integral along the smooth curve C, f dot dr. Now our curve starts at point A and terminates at point B. By definition, this f needs to be conservative. And since it's conservative, we know that we can rewrite that as gradient f dot dr. And that is, as we already know, that f equals gradient little f. Now, breaking this down, thinking about how we would have solved this, parametrizing our line integral, that would give us t equals a to t equals b. Little a and little b are my parameter on t. F is the composition of that vector r of t. Dotted, I'm going to dot this with the way that I redefine dr, so that's the derivative of r prime of t dt, and that is from our definition of line integrals. Now, in order to continue this problem, we need to recall a previous definition from our directional derivative and gradient sections. And what we know is that the derivative along a path is defined as the derivative of that function defined on that path, or the gradient of f composed of the path dotted with the derivative of the inside. And what we can see is that this right here equals that. So I'm going to rewrite my definition, and this is the integral from t equals a to t equals b of d dt of f of r of t dt. Okay, so now this is essentially what our fundamental theorem of calculus says, is that integrating the derivative, you get that antiderivative, or in this case, we would say that's going to be f of r of b minus f of r of A. And so we can very clearly see we use the fundamental theorem of calculus, so that's the same as f of b then, minus f of a, just simplifying our notation. So my jump between these two steps was the fundamental theorem of calculus, and then here I'm just rewriting that as point B and point A. And we're done. Because essentially we proved our fundamental theorem for line integrals. We started with the left and we developed our right. And so that, of course, concludes our video, and we now understand the fundamental theorem of line integrals. We talked about, what that means in a context idea, and then we proved it. We proved that this theorem is true. And that concludes our video. Please feel free to email me with any comments, questions, or concerns.